Passt schon. Ich habe den Pointer da.
Ah, super.
Okay, good. Good afternoon. I'm presenting you some basic information on synthetic aperture radar techniques, methods, and then an overview on radar signal interaction with snow and ice. The radar basics will, for some of you, you will be acquainted with this, but I have seen on the applications that not everybody is familiar with, very much familiar with radar basics. So for some of you, it might be a bit boring. For others, of course, it will be new.
Maybe you have to be a bit closer to the...
Okay, yeah. So it's better now? Okay.
Perfect.
Okay, so this is a contents of the lecture. As I mentioned before, I will talk about the basics of radar imaging system, radar image formation, signal characteristics, and operation modes of radar sensors, radar SAR geometry, which is very particular, and show also the physics and also peculiar features of complex radar backscatter signal, then go on with dielectric and scattering properties of snow and ice, and then switch over to radar interferometry, brief introduction on the basics of SAR interferometry, and show procedures and examples for mapping surface topography and ice motion with interferometry. Now, no need to talk long about that. Here's just for you. I think you all will get the lecture notes anyway, so then you can also look in detail if something is too lengthy here. The frequency bands, I will mainly talk about C-band, 5 gigahertz, where Sentinel-1 is there, then also some L-band example, longer wavelength, 1 gigahertz, and then some, for example, TerraSAR or Tandem-X, with, which has a frequency of 9.6 gigahertz. The transmissivity of radar, yeah, well, that's one of the main reasons we are going for radar, not only the transmissivity of the atmosphere, but also we can also penetrate snow and ice, at least down to some depths. But for the atmosphere, in this example, we see that the clear atmosphere is quite high, at least up to 10 gigahertz, and then it starts to drop. This is a absorption band, a weak absorption band, and for water vapor already here, which can be used for measuring water vapor in the atmosphere. And then I've made here a computation for stratocumulus clouds, which are water droplets, but it's not very dense. And you can see here that once we go to K-band, it plays already a role. Also in X-band is a little bit attenuation, but that's not the full story, because once we have really heavy thunderstorms and so on, and rain pouring down, we have also in C-band, of course, reflection and absorption. Otherwise, we wouldn't have C-band radar for measuring intensity of thunderstorms and estimating rainfall. But this is not so important, luckily, for if we go for snow and ice. So it's not a strong effect, but a little bit impact of clouds, even at least at X-band. Now the basic equation for radar scattering. This is here just to report on the intensity, the measured intensity, which is received by an antenna. This is a bistatic case here shown. Essentially, the wavelength is essential. Then the fourth, the signal power, which is emitted here for a given element, is attenuated by the effector distance to the power of 4. And this sigma naught times area, this is the scattering element, where sigma naught, I've written it down here, is the ratio of received over transmitted signal power, and usually we use the logarithmic scale given in dB. And what this radar cross-section per unit area is usually made up of many small scatterers elements. And this has then a particular impact on the signal which we observe. You will see this produces a speckle effect. Now, the basic components of a SAR system, we have a signal generator, including, for example, producing the chirp, which we use for range measurements, and a stable local oscillator, which needs to be very stable. It's switched forth, and this duplexer means it's switched between transmitting and receiving signal. So there must be exact timing between transmitting and receiving signals. It's then later on split up into two. The wave is split up into two signals, one shifted by a phase of 90 degrees, and another one which is not shifted, which means, and they are digitized separately, I and Q. These are, it's shown here in this diagram. It's called the real part and the imaginary part. So, which means we have an amplitude then, it's a vector, and we have the phase. And in the data we got, we have so-called single-look complex data, which we're going to get, and which we usually use for computing, for example, interferograms. We have an amplitude and a phase signal. So if you get a single-look complex data, you get these two components, and then you can get out the amplitude and the phase. What I didn't mention is that, of course, the distance depends on the time delay, which is sent out here and reflected, and the signal which is received depends on the distance, which is deduced from the time delay, which is 2 times the distance over the velocity of propagation velocity. I will come back to this complex signal later on when we talk about interferometry. Now, a different issue is the image formation. If we go to a real aperture, then the beam is given by the aperture of the this is written by the real aperture. It's written here by the wavelength times the distance of the signal over the length of the antenna, and this will be the azimuth width of the signal in azimuth direction. And then this means that the resolution gets the worse the farther we get away, which is of course not very nice. The resolution across stack depends on the pulse duration, not exactly, because we have then a trick with using a chirp, which means varying the frequency to get a very high resolution, which also will come back to this later. Another issue is, that's quite important, that this is an oblique incidence, the signal, and this is a resolution in slant range, in direction of the radar beam, and this is a direction in ground range, and we can see the steeper the incidence gets, the poorer gets the resolution in ground range. And when we have, on the other hand, for example, if we are near specular reflection, then the resolution is very poor. So this is a real aperture. Here's written again the beam width, its wavelengths over the length of the antenna. Now, coming back to synthetic aperture, there the resolution does not depend on the distance, which is of course very nice. It's exactly given by the half of the antenna length, which means the shorter the antenna, the higher the resolution. Which of course also has its limits, because on the other hand, if we have a very wide beam, we lose the backscattered power of the backscattered signal, and then we start to get into noise. We run into the noise problem. And the range resolution is given, I mentioned before, by the pulse duration times the propagation velocity over 2. Also doesn't change with distance. Now this illustration shows the synthetic aperture, and here the virtual beam width is wavelengths over the antenna length, and then we come up with this resolution along track or azimuth. And this means the longer, the broader the antenna aperture, the longer we can see a point here on the surface. And the virtual antenna length is actually given by the time or the distance as long as we see the point on the surface. But of course, also another point is that in order to catch this very high resolution, we need quite dense azimuth sampling, because there's a limit. It needs to be higher than 2 times the pulse repetition frequency, 2 times the velocity of the antenna along track over the length of the aperture of the antenna. So it's quite tricky to get the right performance which we need. Now, all this comes back and plays a role for image formation. This shows again this, on one hand, this half-power beam width in slant range in azimuth and the large footprint. And now, for the azimuth, we have a wave, the changes of which frequencies, the frequency of which varies between this short pulse. And typically, this is in a megahertz range. For example, with Sentinel-1, we usually have, for white spots, it's in the order of 40, 50 megahertz. We can go up to 100 megahertz even. So usually it's tunable. Even for satellite SAR, you have an option to modify this. And for example, 100 so-called chirp, this is or the range bandwidth. This is the average frequency plus this difference, delta of the frequency. This difference, and if it's the bandwidth is 100 megahertz, we have a range resolution of 1.5 meter. And now there are, for example, X-band radar systems which have resolutions of 50 centimeters or so. There's a certain limit because of the telecom regulations. You cannot go with these bandwidths forever. And then the pulse compression uses exactly the replica of this chirp. So you have and the other would, exactly inverse, and so you can get and pin down, for example, a point target or a target. And this so-called pulse length, which we then obtain, this is a compressed pulse length, is this compressed pulse is 1 over the bandwidth. Then we get this number, this value. And the range resolution is then, I mentioned here before already, c times the pulse duration, in this case the compressed pulse duration over 2. And then we get this so-called de-chirped waveform. This is a range compression. Now in the azimuth direction we also perform a compression, and this is because of a Doppler shift. For example, if we have a point exactly perpendicular to the antenna, then the so-called Doppler shift is fixed at 0, and then from there on the Doppler frequency varies because the range, the distance to this point is different here from the satellite and here. And therefore we get also in a cross-check direction, the change of the velocity provides us the information. One point is with a range compression, we are in the dozens or 100 or so like megahertz range, and with this a long track compression we're in the kilohertz range. It's a much different frequency range. Spectral range, let's say. Now this image provides an illustration on how we get the Rott. This would be an amplitude image of raw data in range and azimuths, and this looks like noise. Then you apply the range reference function, which is a replica of this chirp. Then you come up with range compressed data, which already doesn't look very nice, but you see there at least there are some features. Some bright features have a curvature, for example. And in the next step, we do this azimuth compression, and up here you can see the image data. This reference to Moreira, at the end of this presentation, there's a list of the references. This is a very nice introduction on overview on the SAR basics in one of these IEEE magazines. Now, how does such an image look like? Well, this is a image of a point target, amplitude image in slant range and azimuth. And it's exactly this one, which was a 1.5 meter corner reflector, which we set up in '94, actually, when the SAR CXR experiment had on glaciers here in the Ötztal. And this was Jeff Dozier, some of you may know him, who did the location measurement of this, at that time still with a theodolite. No GPS at the time. And but this was one of the very few, anyway, it was the first 3-frequency radar experiment for Earth observation with X, L, and C band, and still these are still now very useful data, and with field test site also in California and Sierra Nevada and various places. And you see here, this is after compression, there are still side lobes. For example, here in slant range and also in azimuths. So it's cannot be 100% perfect, but there's a difference on the order of 25 dB between the side lobes and the main peak. Okay, the edge length was 1.8 meter. Okay, we didn't carry this up. This was a helicopter, at least. And the pixel spacing in this case is 6.6 times 4.8 meters. And this had a chirp bandwidth of 20 megahertz. And you can see the phase along track. This is a signal variation. This is a chirp in azimuth. And this is the variation of the amplitude. And what is shown here, this would be the raw image of a point target. Then we perform the range compression, which has still a curvature because the distance in the different azimuth points varies across the white swath. This is then the range, the curvature correction called cell migration, and then we perform azimuth correction and get the final image. Now, this ends up with certain characteristics for SAR images, which is in particular the so-called speckle. If you have a target which has many, let's say a pixel, which has different individual scattering elements, for example here, and this would be the wavefront, the front of the radar signal from which we serve the service. Then on one hand, we have a difference from this object to the wavefront, and also the phase due to reflectivity or scattering of the surface of these individual points may be different. Then we get for let's say that's a pixel. We get different amplitude values for different parts of the image, of this element. It's only a pixel, full resolution, single resolution pixel. And we have, for example, we can have interference open. For example, this would be fully constructive interference if this would be a single pixel. This would be, then this is an example of fully constructive interference. All signals maximum have the same phase. This would be fully destructive interference. They cancel out, and everything in between. And this is the case also if we have all these individual points in a single pixel. And it's not only the distance which matters, but also mention also the reflectivity of the target itself sometimes changes, depending on the scattering properties, changes the phase. And what comes up, this would be the phase of all the black arrows of the all individual elements. So then we have a resulting amplitude and a resultant phase, which, of course, is not very useful if we want to look to the backscattering power of the signal, if we have only one single pixel. This is an equation that the total amplitude and phase is the sum, vectorial sum of all these individual contributions in amplitude and in phase. But one point is that this speckle, if we come back, let's say 1 day or 10 days or whatever later, and have the same, look at the same element or pixel, then the phase is maintained, or it looks like noise, but it's maintained if the surface target doesn't change, if the properties of the object. And this is a reason why we can apply interferometry also for this quite complex distributed target. It changes, of course, for example, in vegetation. If we have a wind or if there's snow and it melts, then, of course, we cannot do this. But if the target doesn't change, then the phase is preserved. Now, this ends up with these probability density functions, this so-called speckle. And we have on one hand a spatial statistical distribution of power. Remember the power, the sigma naught, the backscattering coefficients are the ratio of transmitted over received power. For this we have this these type of frequency distribution, probability density distribution for one look, which means full resolution, 1 pixel, which corresponds exactly to the azimuth and range resolution. We have an exponential probability density function. And for the number of looks, look means independent observation elements, resolution cells, we have chi-square probability density function, and the standard deviation is mean value over square root of n. This shows some numbers here in dB. For example, with 10 looks, we have plus 1.2 to minus 1.6 dB. 1 plus 10 standard, 10 for 10 pixel, 10 independent looks or resolution elements. It's different for the amplitude. There, amplitude is the square root of power, and this is the Rayleigh distribution, and the probability density function of the phase of the SAR signal. No, this is not the equation, but it's this is the equation. That's also interesting. The equation for phase for SAR signal of a uniformly distributed target is it's cyclic in 2 pi, so it varies between minus pi and plus pi, and the mean value is 0, and the standard deviation is given over the square root of over pi squared over 3. So this is for the phase, which we then use for the interferometry. Now, these are the equations for the probability density function, which I mentioned before. This is for power here. This would be the case for single look. And this is the Rayleigh distribution for the amplitude. And in order to get rid of this, of course, low-pass filtering is applied, or also already processing over several looks can also be done. Of course, then you don't get the high spatial resolution. That's a problem. And this is an example where we have here a SAR image with 3-meter resolution. It's from an airborne SAR, X-band SAR. It's somewhere in England. It's fields, and these are small trees and hedges, and then this is only 2 resolution elements. And this is now filtering over 11 times 11 windows, pixels, windows with 11 times 11 pixels, which is quite a lot, with a so-called gamma map filter, which preserves the structure. It's a low-pass filter, but it has some additional function, not just block averaging. And this just points out that you can achieve much better results if you use special filters which are tuned exactly to the target which you want to observe. Oliver and Cregan were scientists in UK who did very much work in this respect to optimize, to show how these can be optimized, these filters for different types of objects. And very much development has been going on since that time in this respect because of the many different SAR sensors which came up during the last years. Now, this is an incomplete, but still some example or listing of SAR missions for Earth observation. Just some which we use a lot also for cryospheres. Mentioned here, this would be ERS-1 and 2. And this was really big step ahead, and in particular also in interferometry, because it was really amazing what we could achieve with this one-day interferometry, which was not available for many, many years, and for glaciologists was fantastic data sets. And I remember there was ES2 came up in 95. And in 94 we had a meeting in Frascati, and Fabio Rocca was there and others, and there was a question, how should we do the time sequence between ERS1 and ERS2? And there was two different groups. The one who said, okay, we want to do survey, for example, ocean waves and whatever, and let's go for 16, or would it be 17, 70 days and 18 days. And then there were the interferometry people, very few, and Fabio Rocca was one of those who did really push for this. Let's go for one day. And this was fantastic, because you ever have seen these interferograms because after a few days on the glaciers, it's just gone. And also after 35 days, would have, even if the coherence would be there, the fringes would just have been disappeared. And this was really just some interesting meeting in Frascati. and really a good idea. And then we had the shuttle, and there were also some one day later on short. It was only 10 days, the campaign, but 3 frequency. Then the shuttle radar topography then came, and we saw also RadarSat, TerraSat, and TerraSat-X and Tandem-X, of course, were a very big push forward, also for geoscientific applications. I will show then some examples on this. Cosmos Climate, Sentinel. Now it's a lot. Now this very high resolution, X-band SAR, that's not the only one. ICE-I, there are others. Then in Argentina, SARCOM, the L-band, which has also 2 satellites, L-band satellites, very interesting. And in the future, still more to come. As I mentioned, only very few, which I'm showing here. NISAR, I think the launch is now scheduled for next year, which has a L-band as main sensor. It's with NASA and the Indian Space Agency, and also a S-band with a smaller duty cycle capability, but still very interesting. It's extremely interesting to have these 2 frequencies, which is really a very interesting step forward also for radar science. Then biomass, now I think it's scheduled for 25, the launch, P-band, which has a 0.4 gigahertz. This is quite a significant penetration. It will also be of interest for snow and ice because of this penetration capability, but the main object is forest volume and forest monitoring. Then within the Copernicus program, an L-band SAR will come up, Roselle. I think it's now scheduled for 2027 or maybe 2028 in L-band, complementary to the Sentinel-1. So then we have with a similar orbit, which is quite interesting, this dual frequency, also very interesting for ice, sea ice, but also for other applications. And then the passive C-band SAR, 2 satellite constellations, which will use the signal of Sentinel-1. It's called Harmony, and they also will have a capability to observe digital elevation models, produce, because they have 2 passive SARs, and then you have a single pass interferometry. So also on glaciers, and of course there's still the penetration problem, but anyway, it's useful. But also this will also be of interest for snow and ice, but also for many other applications. Now, I don't think I need to talk about these Sentinel-1 SAR operation modes, because you will hear about this or heard already in other lectures. But just to mention that with these antennas, you can program the acquisition either with high-resolution strip map mode, This is shown here with 5 meter nominal resolution, but a smaller beam width. Then you have the interferometric wide swath mode, which will be the main product, 250 kilometer wide, 20 meters azimuth, 5 meter slant, ground resolution in slant range, which, for example, will be used for the wet snow mapping exercise. And there also is also extra wide swath mode, mainly for the ocean. So this is the advantage of the current satellite antennas. You're quite flexible. You can choose optimum modes for whatever application you need. But of course, you have to agree. And with Sentinel-1, I think it was a good idea to fix it mainly to one given case, one priority case, and this is the interferometric wide swath, because it's very important to have the surveys and repeat observations with the same mode, not only for interferometry, but also for other applications. And I just here noted down that we talked previously about the bandwidth, and we have here, for example, slightly different bandwidths for the different modes between 43 and 56 megahertz. This is because with the but the ground resolution is similar, because here you have a steeper incidence, and here, and then you need a wider band, larger bandwidth to get the same resolution on horizontal ground. Yeah, dynamics is another interesting formation which was used for elevation measurements, and this is only the acquisition modes here. For example, pursuit monostatic, where you have two active acquisitions, then bistatic, where one satellite operates active and passive, and here the signal of the passive of this first satellite, the refracted signal is used. Then there's alternate bistatic and so on. And this is 9.6 gigahertz center frequency. And so I will show then examples for this. And another thing is it's a helix satellite orbit, and then you have different, these effective baselines for elements for a cross-track interferometry, but they change along the orbit because it's a helix orbit, as you can see here. And so you can optimize it what you wish for, only for different frequency zone, and then you change it for the next time for another application. Now, imaging radar geometry is particular. This graph shows the impact of, for example, radar shadow. It's clear. If it's hidden, the signal between a mountain, you cannot see it. Then foreshortening slopes facing the radar get compressed, and the resolution then is smaller. The pixel size is larger in range. And if it's quite steep, or if you look down very close to the nadir, then you get into layover, which means you get the signal from three different stretches along the surface. Here A to C and to B, and from B to D, this on the back slope. And this means, for example, this is an image of, let me show, this is this part of the Ötztal, Upper Ötztal, here's Fendt. This is Ötztal, and you will see here that there are steep mountain ridges. And let's go back here. And you see there's the radar illumination from this side. This is Hinterhälsferne, this is Gebachferne, which is a glacier plateau. And the the ridge which faces the radar is completely compressed, or maybe even reflected into the opposite slope. And the signal is very high because you have a pixel has on one hand close to specular reflection and also the signal of a long, of a much larger area which is compressed. This is a typical layover, and of course this is not so nice, and if you want to get all the information in the mountains, you need to go for observations from different orbits, ascending and descending orbits. This is by the way, is an image with horizontal incidence angle at 30 degrees. Now this shows an example now. Impact, if you have, this is for SAR, because we had here quite different incidence angle here of, here again Ötztal, and here Inntal, and I think Innsbruck is somewhere here. And this is 23 degrees, and this is 41 degrees. And here you have much more layover. For example, Ötztal here, because of the steep incidence, and the slope is reflected on the slope of the opposite side, and here it's not so much. So which means that larger off-nadi angle are preferable if you image mountains. For example, this is near Fendt, this here, and you see here, this slope is reflected in the opposite slope, and here not. This is another example to the area where we'll go to excursion, Hinterdux, on Wednesday. And this is now from EIS. And you can see here, this is incidence angle on the horizontal 23 degrees, which is quite close to nadir. This is a main Zillertal. Here the slope which is facing to the east is compressed and reflected to the opposite side, and this is exactly the opposite. Here it's the slope facing to the west, which is compressed. Now it's time to go on to the snow and ice topic. Now the permittivity of snow and ice, if it's dry, it's a close to linear relation, which is written down here. And this is a real part of the permittivity. The imaginary part is very small. It depends on frequency and temperature, but it's 0.001 or even smaller. So this is really 3 or 4 orders of magnitude below the real part. For dry snow, this is for wet snow, we can compute this by the real part of dry snow plus a term which is given by the volume, water content by volume, times 1 minus the ratio of the frequency over the relaxation frequency of wet snow, which is about 9 gigahertz. This is close to the relaxation frequency of water, but not exactly. And for example, I've written down here that for seabed, for example, for volumetric water content, 6% epsilon double prime, the imaginary part, it's 0.5. And we come up with this equation, these curves that this epsilon prime has this relation slightly different for X and seabed, so it increases. But the real big difference is for wet snow. Here we start with 1 to the power of minus 10 to minus 3, and then we come up with here with 0.5. And this has an effect of the one-way on the penetration depth. It's a one-way power penetration depth depending on frequency, which can be computed by this equation, the square root of epsilon prime over epsilon double prime times the wavelengths over 2 pi. And we can see, for example, we have 4% by volume in X-band. We have penetration depths on the order of only about 2 centimeters, and in C-band is about 6 centimeters or 5 centimeters, and then in L-band it's a bit more, but still it's on the order, it's below 1 meter. This is another one for dry snow and firn. This is now was computed with and measured, and partly derived from microwave radiometer measurements with a radiative transfer approach, where the penetration length reports is the distance where the power is reduced to the value to 1 over E, to 0.37%. I prefer to call this penetration length because some people call it penetration depth, but depth always reminds you that it's vertical, but this is not vertical, but that's always along the beam here. So, and it's given by the losses due to scattering and absorption. And these are measurements, these are really I made measurements it was in '89, in various places in Antarctica and on the plateau in Droning Moorland. And these are these points in the dry snow zone of Antarctica, and they are very similar like the measurements which Christian Metzler made in Davos region. And it shows these are typical average values for dry snow, which is non-refrozen. It may be temperature metamorphic, but not melt-freeze metamorphic. And here at C-band we have 20 meters, we come up to 10 meters at X-band, and then it decreases. For example, in Ka band it's in the order of not much more than 1 meter. But if we have something like this was, I made measurements on extreme ice shelf, where we have this percolation zone, we have refrozen firn. This is firn, and in between ice layers. And when we come much higher losses, and also scattering losses and reflection, and these were data in this area at C-band, where we have a one-way penetration length of 5 to 10 meters, and X-band, for example, from 2 meters to about 6 meters. So just to point out that also this so-called penetration is kind of course be very variable, not just one parameter or one value. Now, if we go on to the beta radar backscatter signal, in this case for dry snow over ground, this is a very simple model, first radiative transfer. We have signal at the snow-air surface, which is a very small contribution in case of dry snow, and then scattering in the volume, and scattering of over the ground, attenuated by the volume, and we have also direct scattering in the volume. So this is a sum of these contributions: air surface, very little, snow volume, and the signal scattered back of the ground, attenuated by the transmissivity, and this is also by the transmittivity of the air-snow interface, and also by the transmission losses of the snow volume. And this depends highly on radar frequency. Now this is here from C-band up to Ku band. This this model computation with a dense medium radiative transfer model, 40-degree incidence angle, assuming grain size 1 millimeters, to show the different contribution for snow mass of 250 millimeters, which would be about 1 meter of our dry winter snow typically before the freezing starts. And then we have here of the signal one here hand of the soil, which dominates up to in C-band, and then in X-band, depending on the morphology of the snowpack, is on similar order, can be of similar order as the signal of the soil. Depends. This is signal. It's fairly rough soil, which I assumed here, and then at Ku band and higher frequencies, it's a clear dominance of the signal of the snowpack. Now, these are measurements which we made here also quite some years ago. This is Leutasch near Seefeld, not so far from here. And these are mean values over winter and spring. And on one hand, for the snow-free case, which is a meadow, rather smooth, cultivated meadow, then these are these triangles. Then dry snow, which is fine-grained, and the dots are wet snow. And you can see that wet snow is, of course, C-band and also X-band lower, significantly lower than dry snow and snow-free. And the difference even larger at cross-polarization. But here, we don't get this signal. For example, because we have a noise equivalent sigma 0 of at Sentinel-1 on the order of 22, 23 dB. And between dry snow and snow-free, there's very little difference. Depending on the roughness, it can be the background, snow-free can be higher, and also on the state of the soil below the snow. If it's frozen, it can be lower, but if it's still wet, if it's not frozen, then typically the signal of the soil below the snowpack, dry snowpack, would be higher. And here in winter, if there's early snowfall, usually the soil below the snowpack remains unfrozen all winter. And in X-band, this difference is even larger, but once we go, in this case, we go to close to specular incidence, then the reflectivity between snow and snow-free and wet snow gets smaller. You will learn about this in the lecture and the practical course on Friday. Thomas Nagler will give you more details to this. Now let's go on to interferometry. At first, I mentioned here the configurations for land, snow, and ice observations. These are not, there are still other interferometric configurations like a long-track interferometry and so on. But I just picked out those which are of most relevance for glaciology. Across track, we get digital elevation models, and we also repeat observation, repeat events. We measure topographic change. Then we have this across track differential, which is for ice motion and surface deformation. We measure the distance, the change of distance in time with the time displacement. Differential mentioned this. This is the change of phase in time due to propagation through a snowpack. You will hear about this also in the lecture on Friday by Thomas Nagler. And this is very closely related to the change of snow mass. And then what we did do also is no time to show this here, is a cross-track multi-baseline photomography. We measure backscatter intensity in terms of azimuth, range, x, epsilon, and also in the vertical direction, and can observe internal structure of glaciers and ice sheets. Some years ago, we had here one of the very first experiments on Mittelbergferner in Ötztal, which was the theory and the computations were done by Politecnico Milano, Andrea Bottiguaneri and his colleagues. And it was really very interesting what to achieve, and this is now in the future also experiments from satellites are planned. But you need very closely spaced repeat tracks of interferometry, several. So you need really a close phase. I think they may have considered this for forest measurements by biomass. They're still discussing this, if they should have for a very limited part of the global area some very phase where they have very closely spaced repeat observations. So that's very interesting for the future. Now this shows again this coherently signal where we have this single pixel, the wavelength and the range resolution, and the difference in the phase is here illustrated, just well known. The interferogram is computed from the complex data, where we have the amplitude, which is the magnitude of the signal, and then we have the phase. And we have these two SAR echoes, amplitude and phase. And then we pick out only the interferometric phase, and the interferogram shows the difference of this phase for the pixel in azimuth and range coordinates. One thing is that what we actually want is an absolute phase, because this 2-pi cycle doesn't help us. And the absolute phase is given by the range, absolute range from the satellite or from a point where we know, can be also on the Earth, where the position is, in geodetic coordinates or whatever, 4 times range over lambda, plus the phase of the scattering element. And what we need is coherence, and for this is computed by the complex correlation coefficient, where we have a sample, we compute this correlation coefficient by the mean value of the whole big window. We compute it, you need to compute this over a window. I will show this on the next slide. And then we get the coherence, magnitude of coherence. This is a magnitude of coherence in the scale. Over this, for example, here's 1 and 2 pixels, only 1 day apart. Again in Ötztal, this is black is very low coherence. Here we have 0.2 average coherence, and this is a snow-free 0.8, depending on the unvegetated areas have the highest coherence. The total coherence includes contributions from signal to noise. These are quantization, ambiguity, and so on. These are processing parameters and data acquisition parameters. These numbers can be kept quite low. This decorrelation with adequate processing. Then we have volumetric coherence and temporal. Temporal is due to changes of the properties of the target, of the object, like wind drift, for example, snow accumulation and whatever. And signal to noise is, of course, if the signal gets closely to the noise floor or maybe even below. This is an example which I did from 3-day repeat bus data of ERS during periods with no snowfall and little wind. And here you can see this is an effective baseline, a cross-track baseline. You can see that the coherence, due to this volumetric correlation, we have here one-way penetration on the order of 20 meters. Two-way penetration would be of order 12 meters, something like that. And then you can see that it decreases, for example, with 400-meter baseline, we have here 0.2 only. And here, this is total coherence, which means that the other factors are not so critical here in this case. Now, I mentioned already the coherence estimate, and there it's necessary to do averaging over a larger window. Here you see, for example, with one number of looks, your large overestimate of coherence. If you go to 50 looks, you're already quite significant. 100 looks, which would be 10 times 10 pixels, it's quite good already. And then here also interferograms with different coherence and different number of looks. And here you can see also the improvements, on one hand with the number of looks, on the other hand with the coherence. With the across-track interferometry, we have phase image. We have the phase is on one hand absolute phase on the range, the distance to the satellite, and given by the, and on the other hand by the phase of the element which you observe. And for full coherence, this phase should be the same. Hopefully, if you want to need a good interferogram, then this should be always quite close. Then we compute the phase difference. It is 4 pi over lambda times this difference in the range between these two satellite positions. And this is the normal baselines on which I will come back later. This is a representation of the phase in the interferogram. It ranges from 0 to 2 pi, either in gray or in colors. And this cross-track inside topographic mapping shown here. We have a signal because the distance changes on the flat Earth, and it changes also on the slope. And all these would be 2 pi differences. And this is the other equations for topography: baselines times elevation over distance times sine of the incidence angle. And this is an equation for the flat Earth. There's also an atmospheric signal, which I cannot talk here now, because if the atmosphere changes, the propagation conditions change, the phase changes, and it's mostly water vapor, which plays a role, which is also usually not so critical over cold areas, but still it can cause some errors if you come over different types, which again calls very much for single-pass interferometry, having both measurements at the same times, like tandem X. Now, I did this simulation for a slope, a cone, a very simple cone, only 500 meters high, 5 kilometers, rather flat. At least if you look at this mountain, it's very flat. This is a simulated interferogram with ERS. It's quite close to near NATO with a baseline of 100 meters. You have here the interferograms on the flat Earth, and then they change once you get to the slope. Now, if you remove the flat Earth, which can be reduced, if you, of course, you have the model of the flat Earth and the precise orbit data, then it looks like this. This would be elevation contours. And then you need to do unwrapping. You stack this up and you come to this coast, which in this case wouldn't be so steep, but it shows in principle how this is, and this interferogram also can then be geometrically corrected. Then you get a map of elevation contours. Now, the sensitivity depends, I mentioned already, on the baseline. The larger the baseline, the more fringes you get, the more sensitive to elevation. On the other hand, you get the problem of phase unwrapping. And this is a so-called height of ambiguity, which is shown here. This is the height for a phase change of 2 pi. And for example, in C-band with 100-meter baseline, here we have a steep incidence angle, close to nadir, 23 degrees, it's 100 meter, and for L-band it's 400 meter. Then there's still another point. This is the INSAR penetration. You measure to the position of the scattering phase center. And this is an equation where you compute it on the volumetric coherence. I will come back to this. Maybe I briefly mention. This is the volumetric coherence which can be derived from the total coherence if you know the other parameters, which are sensor parameters and processing parameters and noise equivalence 0.0. And I did this now in an experiment. I was in 2016. I was on Union Glacier in Antarctica and did this for measurement at several sites with different accumulation rates. There are blue ice fields and accumulation rates up to 400 millimeters, and different points of this region and very different snow morphology. And I came up with this inversion of volumetric coherence for this Z0, these steps of the phase center between 8 meters and 2 meters within a comparative small area. It's near the mountains, the Ellsworth Mountains, very different within a small area. 2 to 8 meters difference, so it's really not easy to get a correction there without this volumetric coherence. I mean, it was area maybe within 30 times 30 kilometers only. And it's also based on tandem X data with different baselines. And this is measurements from optical elevation data, which are based on ISAT and also the REMA, the high resolution optical DM. And they show very close agreement using this inversion. But that's not the only point to do this, because DM difference is of interest. So before I was there on Union Glacier, I did some work with the colleagues at DLR IMF on the Antarctic Peninsula elevation change, and this is part of this area which we covered with tandem XDM differencing. And we they process this data from starting with tandem, co-located single-look complex data, acquired at the same time in the year, frozen ice and snow, with the same sigma naught coherence and same incidence angles, so exactly repeat tracks. So we assumed that the morphology of these glaciers didn't change through that period. This was the assumption. And we did comparisons we had during this, on 3 or 4 of those glaciers, we had differences with NASA-made flights with their airborne tomographic map. It's a LiDAR, a long-track LiDAR. It has 5 tracks, a long track. And we did this comparison, and it shows very good agreement with this tandem X repeat path over these 5 years. The mean difference is only 0.1. It's 1 centimeter, and the root mean square difference, 22 centimeters. We were really amazed that in this case, but we really checked to get same incidence angle, and we were also checked the coherence and the sigma naught, that they were very similar. And this is a point. Otherwise, you need to try to do some corrections, and it's a bit tricky. But if you can have, and it was quite interesting in this case that this was a period when I could talk an hour about this because it's so interesting. I will have a talk on this on Thursday at the Internationale Polartagung in Rauris, because I was supposed to have this as the first presentation today at the opening of this conference, but I told them more important to give the lectures to the students. Okay, well, anyway, this is just a starting point of this story. These glaciers, the ocean was free of sea ice in summers. And we have here a mean for these Larsen B glaciers annual loss of 6.3 gigatons per year. Here we had loss rates up to 25 meters per year in these 2 years. But there's already glacier at the end of this period, the glaciers pushed forward, so rising, the blue curves. And then, this is wrong. This is, sorry, this is 213, 216. This is a mistake, sorry. This is 213 to 216, and we have here 2.9. This was the period when sea ice started to build up, and it lasted this 2021. And here during this 13 to 16, we had already minus 2.9 gigatons per year. But you see that here the glacier terminus advanced already, and overall this, for example, advanced till 2020 by 15 kilometers. And then it collapsed, and within 6 months it retreated by 15 kilometers. And that's what I will talk about on Thursday. So it's very exciting, and that's so nice to have interferometric data, because you have all the area at given dates and firm dates, and no problem with clouds, and so on. And in this case, you will see that here are gaps, and this is because we had only one look angle. So on the foreslopes, we have to exclude, and also on steep back slopes. And now with glacier motion, very briefly come to glacier motion. This shows the problem of glacier motion. This is again this terrace X for with a 11-day repeat with a baseline of 129 meters. It is an interferogram which has topographic fringes, but it's dominated by ice motion. But you can see here that one fringe corresponds to 1.5 millimeters per day line of sight, and we get the motion is not very fast in the calving front, 0.5 meter per day, but nevertheless we get decorrelation because we cannot separate the fringes anymore. This is a point which it's fantastic which details you get on the ice deformation, but if the glacier gets too fast, we run into problems. And this is not really fast, but of course it's a long period, 11 days. Now, the across-track interferometric measurements of surface deformation we measure in slant range only, which means that it includes contribution. This is across-track, a long track, and in vertical direction. No, this is a cross track. This is a view across track here, a cross track view. And this would be the total signal. It's given by the movement component across track, delta y, and then the vertical. And this is made up actually by the following components of the glacier, because if the glacier surface is not necessarily stable, for example, we could have a lifting, if the glacier moves, if there's a dynamic, if a glacier pushes forward, for example, surging glacier, then this adds to the signal. Or we could have melting, then it subsides. And over melting glacier, we can do also interferometry if in the ice areas, actually, so we still get sufficient coherence. And then we have the horizontal shift, the contribution to the horizontal shift, and then we can compute this difference, vertical contribution, surface parallel, due to the surface parallel motion. So essentially, it's made up this horizontal motion, and then this surface horizontal motion projected onto the surface, and then this change of the surface elevation. This shows the sensitivity at the different frequencies. It's quite sensitive. In C-band, for example, 2 pi corresponds to a shift in 2.8 centimeters. Now, to get around this, for example, we would need 3 different measurements from 3 different view directions. which we don't get with INSA, only we have really different tracks which are quite different. So to get around this, many people apply the surface parallel assumption as an approximation for 3D motion, which means we assume that we use data from ascending and descending orbits, and we assume that the point moves along the maximum surface gradient in slope direction, like a water drop. And the surface is stable. Then we get this approach. I think, yeah, and this here is the surface parallel approach, and this would be the full approach here. This case would be the full approach. This one. This is a surface parallel approach, and this is usually applied for interferometric processing, which we also do. For example, when we go for the INSAR, we apply INSAR on the plateau of Greenland, but there it's this deformation in the interior of Greenland. This is at the time scale of 6 days is very small. This is another example still, which Eyjolfur Magnusson from Iceland made in his doctoral thesis here. And this is quite interesting because he looked for water outbreaks and precursors of water outbreaks from the subglacial lakes, like Skeiðarárjökull, the water outbreak from Grímsvötn, a subglacial caldera. And we had only, at that time, we had only this single interferogram. And, but we had from previous dates, we had interferograms from ascending and descending orbits. So what he did, he computed assumed surface parallel flow and computed the direction of the velocity of this velocity vector from stacks of ascending and descending INSAR tracks. These points here, because the direction doesn't change very much at a scale of several weeks. And then he got this. This was a flow path of the water outbreak, and these are this cross section. It's interesting that the water outbreak occurred, started to go ahead around 25 March, and this was on 27 December, the blue curve, and you can see there was on 27, 28 March was already a significant acceleration. Now, but that's not true, 3D motion, and we did some studies with Terrace X. Actually, it was Tandem X, but we didn't apply interferometry. It was Terrace X in Greenland, on Russell Glacier and its surroundings. And here you can see that this was a flow profile along here, along the center line. And you can see here the horizontal velocity was quite high in early. This is here, light blue, in early July, and then it decreased till late August. Here, the black curve, and then it, no, I think this is 8:23. And that it jumped up here. This is a dark blue, this one. And this is the horizontal velocity. Yeah, this 8:23. No, this is, the horizontal velocity, the black one. So it didn't show much acceleration, a little bit acceleration from early August. But that was different for the horizontal motion. For the vertical motion, and was quite exciting because here it was 5 centimeters in July, minus 5 centimeters due to melting. It was minus, this is 0, and here was an uplift in late August, plus 5 centimeters. And the reason was that at that time there was a heavy rainfall, and at that time the intraglacial channels were already narrower than in July, and they couldn't get rid of that water, and so the water filled up at the bottom, and the glacier lifted up. So this is true 3D motion, which we don't get with this surface parallel assumption. And it's very interesting. Now, the surface is just an example for a surface motion project, and we will hear more about this in other lectures during the next days on ice motion. But it just shows from our one of our ice motion projects of NVO, which is based on INSAR and offset tracking. The point is that in SAR we can do work quite well in the interior. We have good coherence, 6-day repeat path images. This is an example. And this is, for example, an ice divide. And this up and down, this is the INSAR signal across this ice divide. No, this is the offset tracking signal, OT. This is the offset signal tracking along the ice divides, which is matching of pixels. And the motion is extremely low. I mean, this is 1 centimeter per day here, this point. And this is an INSAR, which is very smooth, which just shows the much 6-day repeat path, much better accuracy, also, for example, defining the location of the ice divides. But the other problem is when we go to fast-flowing glaciers like Jakobshafen Glacier here, then we need to definitely go to offset tracking. By the way, with 12th day, we run already into a problem during some periods. But with 6 days, this was when the Sentinel-1 switched from 12 days to 6 days, we got every single case. And this is will be this for these outlet glaciers, the fast flows, we use offset tracking and combine this. Okay, yeah, well, thanks for your attention, and we'll be happy to answer your questions. Of course, you will hear this in the lecture on Friday. But I mean, with the phase, because it is not L-band, and also C-band is as a coherence. C-band decorrelates. We did experiments, and also in Finland they did experiments. C-band decorrelates at 3 values typically on the order of 15 to 20 millimeters, in order to buy phase ambiguities at that order. They're also doing in Finland now since 2 years. We have also data. Thomas will show you data. And with L-band, and this is a main point, actually. And of course, also, the point is also that, of course, with this procedure, the snow morphology doesn't play a role. This is a big advantage with the phase delay. All other techniques which go for intensity, everybody, whoever tells you anything, because I was leading several proposals for intensity SAR missions. It was not only CO-H2O, but before already I was cooperating with NASA on other missions. They always showed the experiment large impacts of snow morphology on the backscatter signal. So the grain size. Yeah, and layers, and then melt freeze is a very big difference, or makes also in the penetration. we had experiments here also with. So it's the Canadians go ahead with KU band. So, but they want we'll see how it works out. Yeah. So we'll hear about this on. I think no, the lecture is on Thursday. I think the lecture on this. Yeah.
I'm interested in glacial elevation changes, and you showed your study on the Rott Peninsula, and I think we saw quite a lot of white areas. Are these data voids?
This is points when you go to four slopes. These are steep slopes, partly without, or mostly without ice even. And yeah, you cannot go, you have seen before than four slopes, and if it's very steep back slopes. And some of these gaps, also I could show you curves on the elevation dependence of, we have very detailed analysis for filling these gaps where ice is and so on, and compare this also with the optical, and it agrees quite well. But this is of course a constraint always with the radar view directions. So, anything else, or time for coffee break?
How do you misbehave the snow in order to detect it in comparison with bare soil? So,
Yeah, with which technique?
exactly. I don't know anything about SAR.
So, with SAR, if you go to, I mean, the question is always a trade-off. With SAR, you don't have to care about morphology. But if you go to higher frequency, of course you could, they do, for example, there are papers also on using X-band if you go to higher latitudes and so on. You can, actually what we do is detecting changes. So we have time series with the experiment here near Kütai. And we measured, for example, snowfall in C-band and even in L-band with it was 12 millimeter snowfall. And we got an agreement on the order difference of 1.5 millimeter only to the field measurements in 3 areas, and we did detailed transects in the field. So, because it's a change of measurement. So it depends very much on the accuracy of your system. This was with airborne data, with a campaign with a DLR SAR.
I've got another question according to SAR, so I'm not that into the topic of SAR, but you need to figure out the atmospheric parameter to get the signals, and what are the main...
We found the
atmospheric parameter to...
You don't need to if you have done them, because the interferogram, you have the same atmosphere when you generate the DM, because it's tandem X.
Okay,
It's
because they are like...
yeah, following within... No, the baseline is only the orbit. They have the same orbit, but they are very close, also in time.
But they're like, I thought there would be like inside methods, or you've got like temporal baseline.
No, the temporal baseline is close to 0 for tandem X, because they are along the same orbit in the helix. This is a nice thing with this mission. But also otherwise with, I mean, in the cold atmosphere it's not so critical, but it's nice, of course, much better to have it's this bistatic systems. It's a bistatic system, more or less, yeah. Okay, I think what's the time schedule is, I don't know. Yeah, I think the next lecture is. Is coffee break now? Or?
Yes, we have a coffee break now.
Yeah?
Coffee break now.
Is the time now or later? Okay, then it's now. Okay. Yes.
Why the velocities are increased a lot? When
No, it did not. Yeah, we couldn't get, because it goes farther to the front, we couldn't get this fast velocity data.
So it's
No, this is also a different period. This was a different year.
and because it increased.
No, it wasn't. No, we couldn't get this fast velocity data.
Oh, during this 12 days interval.
Yes, they are missing. They are missing here.
Oh, so when it's
They are missing. These are missing.
okay. Thank you.
What do you think the offset tracking is less low velocity than inside?
I mean, this is still enormous. I mean, 1 centimeter with a pixel size of 20 meters times 5 meters. How would you?
That's
Single
different.
pixel size and you use larger windows.
Right.
It's still amazing.
Yeah. that's it. Okay, thank you.
Because you're matching really large plots.
Yeah. As I never use the offset tracking now, we'll then use the inside. But thank you.
It's really, ice divide is close to, this goes close down to zero, the ice divide.
Right there.
Where they do usually the quarterlies than the ice divides.
So that means right here, right?
Yeah.
Thank you.
I am Sarvesh from India. So I have some little doubt. Like when we measure the snow depth using the SAR, when we measure the snow depth using the SAR, and we compare it with the ISAT2, how much good it is to compare our results with the ISAT2?
With ISAT, they have a big problem on the slopes.
Yeah.
Their publications, you may know. On the slopes, they don't do it. Their publications also, like in California, so now in the other places, and they on the slopes it doesn't work well. If it's flat, it's okay, but on the slopes it doesn't.
In mountain it will not work.
Yeah,
In flat
yeah.
area, if there is snow, then it will work.
Yeah.
Yeah.
You can find their papers, their publications on this, where they investigated also dependence on the slope. It's in the open literature.
Thank you.